Okay, I'm going to try and do this as quickly as possible. Please don't forget, if this is too fast for you, all of this information is provided in the slideshows, and much of it you will be able to go over by going through the different videos on the naming playlist. There is a playlist up on YouTube that is just my videos on naming. Here is what I think are the top questions about balancing charges, and the first one would be why, when do I need to balance charges? You only need to balance charges if the compound that you have identified is a name, not a formula, and you have determined that that compound is ionic. Okay, and for our definition currently, that means it either contains a metal and a nonmetal, or it contains polyatomics. So it could be made of polyatomics, it could just have one polyatomic. Whatever it is, if it's not binary at this point, it's going to be an ionic compound. Where do you get information about the charges that you're going to use when you're balancing? So when you're balancing, you're going to be using a basic knowledge of the periodic table. That means that you're going to be pulling that off of the periodic table that you're given in class. You may have labeled this on your periodic table. Let's just pull up that periodic table for you. On your periodic table, you should have some what I would refer to as common charges labeled on your table. Okay, those are not always going to be true, but they're true a lot of the time. And so at the college level, you're not given charges on the periodic table, so we memorize them just like this. We divide the table up into main group elements and non-main group elements. Okay, your non-main group elements are these guys in the middle. You know them as the transition metals. So your main group elements are groups 1 and 2 over here, and groups 13 through 18. Now, right away, also, you're going to notice that 18 being full of elements who don't make bonds, and so won't usually be in compounds. There have been some situations where they were bullied into it by some chemists. It goes like this: 1 plus 1, 2 plus 2. Okay, 13 plus 3. Do you notice that the charge is lining up with the second part of the group number? Plus 4. And then at group 15, you're going to start to count backwards. So minus 3, minus 2, minus 1. Now, you do need to be able to assign these charges without looking at a table so that you can get it down pat, right? So you will notice that there's a whole bunch of charges listed. This is the Regents periodic table that I won't let you have yet. And the reason why I don't want you looking at that is because can you imagine how much more confusing this would be if you had 8 different charges in front of you and you really didn't know what to do? Where it will be helpful is here over in group 1. You can see group 1 only has one option. They're all plus 1 charges. Group 2 only has one option. They're all plus 2 charges. And so you'll see that a lot here. Group 13, it's very common also up until you get to TL. That is something that we can kind of rely on. So right now we're using charges they commonly use in common compounds. But again, those compounds have to be ionic. All right, let's go ahead and erase that and move on to the next question, which is, let's make sure you can see that. Okay, so far we know that if we can't identify a name from a formula, or we can't identify a compound as ionic, we won't know when we should balance charges. So you might be balancing charges on molecular compounds. That's not going to work. Or trying to give molecular naming rules to ionic compounds. That's not going to work either. Okay, so now where do we get information about charge? I just showed you common charges, which are on the periodic table. You also will find information about charge on your polyatomic ions. So you had 6 you were supposed to memorize. Those will be given to you now on table E. Just because you have table E doesn't mean you're going to have an easy time figuring out if a polyatomic ion is there. But if you've reviewed them a lot, you should be able to use table E pretty fluently. So let's get to the more difficult situations. The simple situations is, what does simple charge balancing look like? That's going to be a situation where you have a compound that's easy, like, I'm going to go ahead and type this. A compound that I would consider to be easy would be two main group elements bonded to each other. So like sodium and oxygen, which in a compound would be written as oxide to show you that it is bonded. Okay, when you're doing this, you're going to find out your common charges. You're going to make sure you know that sodium is a group 1 metal. And you will find chlorine or oxygen, sorry, in group 16. That gives sodium a +1 charge and oxygen a -2 charge. Okay, your job is to make sure that these charges add up to 0. You cannot forget that even though we're only talking about 1 sodium and 1 oxygen, in a situation where these two would be bonding with each other, they would be in a crowded room full of other sodiums and other oxygens. Okay, so essentially, oxygen's going to be able to pull the same amount of charge towards him, but the opposite charge. So if he's got -2, he can attract +2. So if people only have a +1, what will just happen is he'll be able to attract 2 of them. Okay, so +1 and +1 is +2, which cancels out a -2. Once I'm done with this process of getting all the charges balanced, I'm going to count up what I came up with, and I'm going to write my final formula. So 1 sodium, 2 sodiums, that would be in a subscript. I would write, I have 2 sodiums in this compound, and then 1 oxygen. Okay, so if you're confused about what all these numbers mean, first of all, I think you're showing me that you haven't practiced, but there are detailed slideshows on this. There's a slideshow on chemical notation, and it's important that you follow the slideshow cues, the ionic slideshow. There is also a video of me going over that lecture. All right, when does charge balancing become difficult? There's a couple of different scenarios you might come across. One typical scenario would be if you come across a situation where the charges don't balance that easily. That's a bit of a pain. That would be a situation like if I run into somebody who has a +2 charge, like my compound might be calcium, phosphide. All right, phosphorus being in group 15 will typically have a -3 charge, and calcium being in group 15, group 2 will typically have a +2 charge. So this is going to put me in a weird situation. And my weird situation is that this is not clearly obvious how I'm going to balance these. So I end up in a scenario where I have to keep adding them until they come to a common number. So you could see right away, right? I could try adding another calcium. Now I have 2 calcium. My charge is still never going to add up to this -3. I now have a +4 and a -3. That's not really helping me. So even if I were to add another phosphorus, now I have a -6. So my job is to bring them to a common multiple. So I'm going to go ahead and add another one of these because the common multiple of 2 and 3 is 6. And you're going to see this scenario come up over and over and over again. Another example might be if I had like an iron with a +3 charge and an oxygen with a -2 charge. Even though the +3 is on the metal this time, the 3 is on the metal and the 2 is on the non-metal, I'm going to end up with the same situation, right? So when I write these, I'm going to have to do a little more work to count it all out. There is a little bit of a trick to this one, but I don't like to teach it because it often confuses people in other scenarios. 1, 2, 3 calcium, I'm going to write Ca, I have 3 of them, and 2 phosphorus, I have 2 phosphorus. Okay, so keep in mind that these numbers on the bottom, people who are still making mistakes, a lot of you are making mistakes because you don't understand the difference between this number and this number. Okay, this is a charge. This subscript tells me how many phosphorus I put in the compound. All right. Another situation you might run into where balancing becomes difficult, because for you guys, especially if you haven't practiced your polyatomics a lot, you might find it confusing when you run into a situation like sodium sulfate. Okay, I'm going to see this ATE ending and I am going to be like, ding, 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 that's a polyatomic. Okay, polyatomic ions come as sets. And each set of atoms, their group, have that charge collectively. So in this case, the subscript shown in the polyatomic does not affect the charge calculation. Okay, so what I often do when I'm teaching this is I will say, okay, well, sodium's a group 1 metal. Sulfate, I have either memorized it or when I see this ATE ending, I'm like, oh, I better go look that up on table E. You have to be really careful though. Table E, sulfate has a neighbor who looks a lot like him, but is not the same and has the same charge. So you have to watch out that you don't put sulfite instead of sulfate. It's a very common mistake. Okay, so SO4 has a -2 charge. So what I mean by this is these come like a pair of socks that are stuck together at the store, right? You can't take the two pairs of socks apart and be like, can I just buy this one sock? No, no one's going to let you do that. Okay, so they come as a group, and that group has this charge for the whole group. So these subscripts are different in some ways because they're describing people's grouping. This is why polyatomics are very hard to recognize and very hard to read for beginners. As we get further into bonding theory in third quarter, we're going to get into a lot more detail about what these guys look like and maybe even a little bit more about like why they do this. So when you're dealing with the group, you don't increase the number of polyatomics by changing this subscript. You leave this whole set alone. And just like you do with the other guys, you just add more of them or less of them. Now, in this example, which I probably shouldn't have picked, I'm actually going to need 2 sodiums here to balance this charge out. But what if I got a different situation? What if I had magnesium with a +2 charge and hydroxide, a polyatomic with only a -1 charge? This creates a problem because if you, you know what, let me not even use that example. Sorry, you guys. I want to pick somebody who has a subscript so that I think, because what I think is happening is that this is visually confusing for you. So say I go to nitrate. Nitrate has its own subscript and a -1 charge. Okay, if I'm going to balance this, I am going to need a second negative charge to balance out this +2. What I have to remember is that these guys are stuck together. I'm not touching this subscript the way I would with other situations where they're single atoms. So I'm going to go ahead and put a second nitrate on there. Now I have 2 minus charges and 1 +2 charge, and they are balanced. Then there's the part where I have to actually write that out. So I'm going to say magnesium nitrate. Nitrate just looks like that. And I want to say that I have 2 of them. The problem is if I write it like that and I understand chemical notation, whatever is to the right and down is the subscript that applies to just this atom. If I write it like this, it looks like I have 32 oxygen. And I don't mean that. What I mean to say is I have 2 nitrates. So I'm going to put a parentheses around this so that I could say I have 2 of everything inside these parentheses. So you could see naming is really very much about communication. Okay, so I'm communicating to people, I have 2 nitrates. All right, the other situation that you might run into is when you have to work with charges backwards. Okay, and that has to do with the whole transition metal problem. So the transition metal problem is that transition metals have multiple charges. So if I were to go back and take a look at the periodic table with the charges on it, which I sort of fundamentally disagree with giving to you because it only actually makes things more confusing. If I were to give you this table right up front, you've just got all these other things going on. And it's really hard to see when am I using certain charges and when am I not. If I don't give you this table until after you've memorized that the rules are only people who live in the middle and some exceptions get Roman numerals, and most of the time people like nitrogen are going to be using a -3 charge, you shouldn't make as many mistakes. You're going to be able to see what are the clear-cut rules and what are the exceptions. Okay, now here are the transition metals, and here are all their charges in all their glory, right? So if you were dealing with titanium, you would have a choice of 3 different charges. But the problem is it's not actually your choice. It's their choice. And that choice is made, maybe it's not a choice, but it depends on who they bond with. Okay, whether or not titanium is going to lose 2 electrons or 3 electrons or 4 electrons depends on who he is bonding with and the situation the bonding is occurring in, right? So sometimes these reactions happen differently under different conditions. What he might do under cold conditions, he might not do if you heat him up. So the way you're going to determine which of these charges he is using is by the person he has bonded to, because that's determining how many electrons he's actually giving up to get his charge. And again, we will go over this in a lot more detail when we get deeper into bonding. But what you need to know right now is that everybody who lives in here, unless I tell you otherwise, like, so for example, these guys all have 1 charge. People like zinc and cadmium only have a +2. Silver only has a +1. Those people typically don't require Roman numerals, but people who get more than 1 charge, and so there's some other sneaky people over here. Tin, bismuth, and lead are all metals that have more than 1 oxidation state. So I call these guys MMOSs, metals with multiple oxidation states. Oxidation state, fancy word for charge. Okay, fancy word for charge. So when you run into these guys, you have a situation where you have to communicate to other people what charge they are carrying. Now, if you are looking at the formula, you can always figure that out. And so you don't really actually have to worry that much about whether or not you can figure out the charge. Where you're going to have to worry is if somebody were to give you a name without a charge, right? So when you're doing ionic naming with transition metals and you get the name, you're actually totally fine. You don't really have to worry all that much because they're going to tell you what the charge is. I'm going to write it for you. It would look like this. Right? Because the person who wrote this name for me knows that iron has 2 possible charges, they're going to do me a nice favor and they're going to say, hey, I'm letting you know that this is the iron with the +3 charge. That's what that 3 means. Okay, so that when you're writing the formula, you know if chlorine has a -1 charge and you balance this out, it should be FeCl3. Okay, I had to put 3 of these to balance that out. I'm jumping ahead because I hope that you understand that part so far. Okay, where you have to do the annoying thing is if you're the one given the formula. Okay, so the annoying thing is if you're the one given the formula, if somebody says to you, oh, this is Fe2O3, you're the one who has to figure out the charge and put it in Roman numerals so that other people know. And that means extra steps for you. The very first step that you have to be aware of is that you need to recognize that this is a metal that could have more than 1 charge. How do you know? It's probably in the transition metals, or it's one of the 3 exceptions. That's lead, Pb, bismuth, Bi, or tin, which is Sn, is a nice Latin name, just like lead. Okay, those ones you have to write Roman numerals when you do the name. So for your first job is to do the charges backwards so that you can figure out what charge iron is using here. So you're going to work off who he's bonded to because that's who's causing his charge to be what it is. Okay, so I'm going to go ahead and break this up. I've got 3 oxygens, each with a -2. And that is the common charge that I know from it being in group 16. Altogether, this is coming together as -6. The rules say that when a formula is written, everybody has to add up to 0. And so that means that whoever's here has to be adding up to a +6. Second problem, though. The second problem is that you have 2 irons. So if you get more than one of them, what you need to do is divide the charge up evenly between them. So if you have 2 irons, that would mean each of these irons has a +3 charge. So it's your job to write, this is an iron with a +3 charge, oxide. So that the person who has to write the formula knows what charge they're using to balance it. Okay, so hopefully that answered everybody's questions. Polyatomics, they're always going to be difficult and visually confusing. They don't get clearer by using the other ones off table E. Unfortunately, they only get more confusing. But just keep in mind that polyatomics always have to stay together. You're not allowed to separate them, and their subscripts come with them. So you're either going to just put more of them and balance their charges. Right, I think that's short. I hope that's short.